Today we study Young's experiments. First, we consider a plane wave. This is a plane wave. This is a plane wave that propagates along the x direction, positive x direction. You can see a wave is oscillating at a certain point. The height represents the displacement of the wave at a certain point, and it is oscillating. It is going up and down. And any point that has the same amplitude and same displacement, we say these are the wavefronts, or that displacement can be interpreted as a phase. Any point that connects the phase are wavefronts. At the wavefronts, the shape of the motion of the wavefronts is related to the velocity of the wave, and right now this wave is propagating to the right. The direction is along the x-axis, so it propagates along the x-axis with a certain velocity. The velocity can be computed by displacement divided by time, and we can choose a point of equal phase. It is traveling along this direction, and the duration of time that propagates along the same direction to the wavelength, in the dimension of the length. This is the wavelength, and the wavelength divided by the time is the velocity of the propagating wave. We can see at any point that the direction of the propagation is parallel to the x-axis. This kind of wave is called the plane wave. In addition to plane wave in general, source of a wave can be a point, and oscillation. And initially, the medium is flat, and we perturb a point of medium to find an oscillation that propagates all over the direction. For example, this is a wave originating from a certain point on a plane, and we can see the wave propagates from a single point to everywhere. The direction of propagation at any point that depends on the direction, the radial direction that connects to a point to the origin where the source of the oscillation is present. So the radial wave, it propagates radially everywhere in a uniform way, because the area of, for example, circumference of the wave depends on the radius, so the amplitude at each point decays as r increases. Anyway, this radial wave is propagating from a certain point to a radial direction. So let us consider superposition of two waves. This one shows the two sources of the waves. The radial wave is oscillating in a simultaneous way. The two phases of the two sources are equal. Then we say they are the two sources are in equal phase, and it is is also called coherent wave. Previously, we have seen a propagation of wave from a single source, but in here we have two sources. They are oscillating simultaneously, and the left one and right one are of equal phase. The result of the interference becomes a rather complicated wave structure, but the calculation of the resultant wave is quite simple. It is just the sum of two waves. In case they are in opposite phase, completely out of phase, one when the left one is down, the right one is up. Because the structure is too complicated, it is not easy to distinguish the interference pattern of this case in comparison with the in-phase case, but we should find it rather easily later. Young's experiment is like this. We have two sources of waves, and they are coherent. Coherent means that their phases are of equal to each other. To make a coherent phase, we usually begin with the incident wave, that is a plane wave. This red line, each red line represents the wavefront. The wavefront is the line that connects the points of equal phase. And the same phase appears when we go further by a gap of the wavelength, and it appears repeatedly. If the line then connects the points of equal phase, that is wavefront, if the wavefront is a parallel line, that means our wave is plane wave. So every point in a single red line along a single wavefront of equal phase. When it enters into a hole, remaining pieces will be absorbed or reflected. Only this part can propagate further along the original direction. If it were a particle, it would have traveled along a straight line. However, because it is a wave, it propagates radially from this hole. This effect is called the diffraction. The diffraction is the well-known characteristic in comparison with the particle, but we shall find if we learn the quantum mechanics, particle also has the wave nature. But anyway, in the Newtonian view, the particle goes straight if there is no additional force and no external force. So, to distinguish something that is moving is whether a wave or particle is to identify whether it diffracts or not. Considering the diffraction, the computation of diffraction is straightforward if we applied Huygens principle. And if you learn Further, if the whole size of a hole shrinks, the magnitude of diffraction increases. I mean, if the hole is large enough, it will go ahead similarly to the plane wave, but as the size of the hole decreases, the transmitted wave behaves more like a radial wave. That is the striking difference between the small hole and large hole. From now on, we call this hole as a slit. Let's see. Here there is a source of the radial wave, but it is not a really radial wave because just before it enters this point, it used to be a plane wave moving upward from the negative to the y-axis. And as soon as it passes, the left and right part of the wave disappears, and the only source of the wave is the oscillation of the medium at a tiny point. And from this on, it propagates radially. In actual numerical calculation of this animation, we used 11 point sources. They are of equal phase, and we added them all linearly. And as we can find, this gap is small enough. This gap is the size of the wavelength of the wave. It just like move along the radial direction. And this one is the case for aperture diameter A is equal to lambda. That is the wavelength. In case if we increase the width of the slit, you can find it is more or less flat. It is similar to plane wave near the hole, but at the end of the day, it propagates radially. But curvature differs. It is more flat in comparison with a small hole. This aperture A is 3 times the wavelength. If we increase the width of the hole further by 5 times, you can see the hole is wider. Now for 1, 2, 3, 4, 5, more or less 5 sources seen. In the middle of the hole, it is propagating more or less flat, so it's similar to a plane wave, but in a global sense, it is propagating radially. However, the curvature is rather flat when the hole is bigger. This is the basic nature of diffraction of wave. Young's experiment make use of two coherent waves. Two coherent means they are of equal phase. In order to make a coherent wave, we prepare a source of the wave as a plane wave and let it pass through a tiny hole and of equal distance to S1 and S2. There's an additional screen on which there are two tiny holes are placed, and the distance of the 2 points and distance of these 2 points are the same. In that case, the radial wave coming from diffracted from a single hole are of equal phase when they arrive at S1 and S2. Then now we have prepared the two coherent waves and let them propagate to the screen. That is, it is rather exaggerated. Actually, the distance from this plate B to the screen C is rather very large in comparison with the distance between the two slits. For the time being, we assume that the width of a single slit is infinitesimally small and very tiny, so we ignore the size of the single hole. In that case, the distance between the two slits and this is very important to analyze the interference pattern appearing on the screen. As we have already seen in this case, two coherent sources produces wave, and then we can find the interference pattern. In some case, if we average over time, this displacement from the equilibrium position is now expressed as the contour of the strength of this oscillation of the resultant wave. If we take the time average, because it is a periodic motion, then we can find the place where the amplitude is magnified, amplitude it becomes very small. So the relative importance of the amplitude or the strength of the wave can be described as a fringe if we use the light wave. When the two light wave interferes, when they are completely in phase, the intensity of the light wave is magnified. However, if they are completely out of phase, they completely cancel and the intensity becomes zero. So here, what the fringe means the strength of the interference of the resultant wave. Okay, so we can observe the intensity of the light that will become wave in nature, the fluctuation of the intensity on the screen. Important point in this experiment is we have to make use of monochromatic wave. That means the wavelength lambda is fixed. And S1 and S2 must be in phase. In order to make them in phase, we prepare a single source, and the distance between S0 and S2 and S0 and S1 must be the same. If we do not make use of this kind of tool, recently the laser is produced. The laser produces a coherent light, and we can also make use of laser to reproduce this experiment. There are bright bands This is related to constructive interference that magnifies the resultant wave, and dark fringes represents the points where the destructive interference occurs. We say we have a terminology. Interference pattern means the bright and dark fringes on the screen. The time average. This picture shows the displacement of each point depending on time. But if you average over time, we can find some distribution. This is the result. When we use here, the following plot shows the interference pattern of Young's experiment for d equals lambda, d equals lambda, and d equals 3 lambda, and d equals 5 lambda. Previously, when we considered this was a aperture diameter was a 5 lambda. That means that this is a single slit experiment with a very large hole, but the Young's experiment uses two tiny holes that are separated by distance d. Separated by distance d. This is d, and this is d. And d equals lambda, and d equals 3 lambda, where lambda is the wavelength, and this is d equals 5 lambda. Interference pattern. This interference pattern can be observed in this experiment. If we cut somewhere, we say the distance capture d from B to C, so capture d. If you use capture d, then capture d is this one. The small d is the distance between the two apertures. Then you can find the bright, dark, bright, dark, bright, dark, bright, dark. At the same distance capture d, you find bright, dark forever. Here, d, same d, about 6. So bright, dark, bright, dark, bright, dark, bright, dark, bright, dark, bright, dark, bright, dark. So these are the fringes, and you find this gap between the two adjacent bright points. This one. This amount increases as d. This is large d, large and small d. As this d decreases, the width, the gap between the two adjacent bright points increases. Here, one cannot observe the next bright point, but we decrease the capture d, we will find this one, and bright, dark, and so on. All right. The next problem is to relocate the fringes in Young's double slit experiment. This is fact by experiment. We would like to interpret this result theoretically. Let us find out the position of fringes. In Young's experiment, we have two light sources. They are coherent. They are completely in phase, starting from the two different positions, and two radio waves propagates from the two slits, and the two light waves interfere at a certain point P on the screen. The light wave has a structure. The wave function of the light wave can be represented by the electric field, and we know that the electric field satisfies the wave equation. And solution to this wave equation is some amplitude times e to the I k dot x minus omega t. And two sources, we have S1 and S2. The electric field coming from this wave, we say we have E1 vector, and another electric field coming from the aperture S2 is E2. And the resultant electric field is the sum of the two electric fields. We shall find it is proportional to this, and we have time-dependent vector. They are completely vectored out, and we have I k dot x1 plus k dot x2, where this is a vector x2 and this is a vector x1, something like that. Because these two waves are of equal at 2 points, there is no difference at all. Therefore, the phase difference of the two electric field E1 and E2 comes from this part. That we look into the path difference of the two waves more closely. The light wave coming from the source S1 travel along this path S1P, and the other one travels from S2 to P. And if we consider k dot x, and if distance d is large enough, then we can approximate that this is almost this R. R is very similar to D, and it's just much bigger than small d. This figure is a little bit exaggerated, and in actual cases S1, S2 are very near, and this R1 and R2 are almost parallel. So let us consider the path difference of the two waves. Because they are almost parallel, this triangle can be interpreted as this one. Both of them are almost right angle. The theta approaches 0. Okay? However, theta is not exactly 0. It is tiny. the path difference of the two light waves can be calculated in this way, because from to here to there, S2 to P, this distance are almost the same. So we ignore the same distance, and the only distance that makes difference in the phase contribution as exponential ikxt in here, this is that gap. This path length difference is called the delta L. And if we magnify this tiny triangle, we have angle theta. This is the angle theta, and this angle is also theta. This is the distance, perpendicular distance, and this d is the gap between the two apertures. This is a right triangle, so path length difference delta L is d sine theta. D sine theta is the path length difference. If the two waves of different path lengths, exponential I, let me approximate this k is parallel to x vector. X vector is almost a parallel vector connecting the center to the center of the aperture, so to the center of the screen. This is kx. Kx is exponential two pi or lambda, and we have delta x. So it's exponential 2 pi I 2 pi delta x over lambda. So this vector is crucial. If the path length difference, this delta L represents a delta x in this expression, and if delta x is a multiple of wavelength, then m times lambda, and m is the integers. Here m is a positive, m is a negative, and central point m equals 0. Then we may have the maximum points, because it is two waves of equal phase. So this is a constructive interference. On the other hand, if the two waves are completely out of phase, that means their phases are different by 1/2 lambda or 1/2 lambda plus n lambda, where n is an integer. We say it is a half integer. Integer plus 1/2 is a half integer. In that case, it is a completely destructive interference that results in dark fringes. If we substitute these values and solve the angle, then we can make use of arc sine function to find out the places where the bright or dark fringes appear. If we consider the aperture is very tiny, so we had better use special units. For a unit of a tiny number, we recall this table of SI prefixes. So recall all those numbers. We are familiar with large numbers, mega, giga, tera, peta, eta, zeta, exa, zeta, iota, and small numbers, milli, 10 to the minus 3, micro, 10 to the 1 millionth, and nano, 1 billionth, pico, 1 trillionth, and so on. Femto, atto, zepto, yocto. But you should be familiar with those numbers. They are pure numbers, 10 to the something. So let us reconsider the same experiment, but with the physical numbers in our K-pop collaboration experiment set B8. We have these kind of similar numbers. We use the wavelength 650 nanometer as a deep red laser diode, and PY is in here. The distance between the two apertures are in millimeters, 0.1, 0.25, 0.5, something like that. And distance D is, for example, 1 meter. If we substitute these numbers explicitly, we can find the distance y on the screen can be computed in such a manner. And these are the numbers measured in a real experimental class. So let us review what we have done until now. We used coherent lights. Coherence means the two wave sources are completely coherent. There is no phase difference. If they have a constant phase difference, the common frequency and common wavelength. Common wavelength and common frequency is the most important one, and we usually use the completely in phase sources. The light from the slits S1 and S2 is completely coherent. The preparation of coherent light was obtained by placing a single slit with equal distance to the both apertures, or by making use of a laser. And using that coherent light, we are able to identify the maximum and minimum point. This calculation was quite simple because there is a big assumption that the tiny hole's size can be neglected, and all of the contribution in a single slit is completely determined as something like kx, and this value is a constant in this approximation. Later, in the next section, we also consider the phase difference within a single aperture. Okay, let us consider intensity. The two light waves, before we make use of a phasor method, we can still make use of sinusoidal wave function for the electric field. The two electric fields with in here we have factored out the common kx part in the exponential I kx minus omega t style. Factored out the common factor, and for example kx1 plus e kx2 minus omega t, and we factored out I k x1 1 plus e to the I k x2 minus x1, and this one was assumed to be delta L, something like that. And additional factor is e to the minus I omega t. And this part is considered in a phase difference in the time-dependent way. So the computation can be done within the time space where the phase difference is inserted in here for the phase difference between the E1 from S1, E2 from S2. The phase difference is just like what we have done, the 2 pi d over lambda sine theta. Path length difference d sine theta. d sine theta. Okay. So if we add these two electric fields, what we find is over vector E1 and sine. When we add the two signs, this one can be decomposed into omega t, and omega t plus phi means omega t plus 1/2 phi minus 1/2 phi, 1/2 phi plus 1/2 phi. What is omega t? Is omega t plus phi equals. So this one can be expressed in this, and this one can be expressed alpha minus beta and alpha plus beta, where alpha is omega t plus 1/2 of pi, and beta equals 1/2 of pi. So by making use of the expansion formula for the sine alpha plus beta and sine alpha minus beta can be computed in an easy way. The result is 2 times E0 is factored out already, and 2 times cosine half of phi multiplied by, the square should be neglected. Okay, the resultant wave has this common phase is a sine, and this one different phase. This contribution appears as an over a factor of cosine 1/2 phi. At a this part is depending on time, and for a given time the electric field is given like that. We know that the electric field propagates along a certain direction this way, and 3 dimensions we have electric field, magnetic field, this is the propagation of the electromagnetic wave. electric field oscillating on this plate, magnetic field is oscillating, and electromagnetic field energies are propagating along this is x, y, then along the z-axis, the energy is propagating like that. So the energy density corresponding to the current density propagating in space can be expressed as a Poynting vector, as we have studied already, and the energy deposit in a certain area is the total energy deposit to an area. Actually, the energy per area is per area, and per time is expressed as the energy density intensity due to the electromagnetic field. So, although we have computed the electric field only, the magnetic field contribution can also be computed in a very easy way by making use of Maxwell's equations. And we know they are completely in phase, that when we compute the energy density, then we compute the electric field energy density. And magnetic field energy density. And the sum. And this one is expressed in terms of this intensity. Here we have to average over time, and this one is a sine omega t plus 1/2 of pi. This is a e squared, so sine squared average, that is 1/2. That produces this factor 1/2 that result in the RMS value at the amplitude level 1/√2. Anyway, this is the reason why we have not included the time dependency in the previous analysis, identifying the local maximum and minimum points. So if we remove this time-dependent part by averaging over the time, the intensity of the electromagnetic field deposit to the screen is proportional to this one. And here, this amplitude contains the phase-dependent part, that is 1/2 cosine 1/2 pi. At the amplitude level, but at the intensity level, we have cosine squared 1/2 pi, 1/2 phi. This one is something like that, and this is cosine square. It becomes here is the position where cosine of a phi equals 0. So we can find the solution for the local maximum and local minimum. Local maximum of the intensity will appear at these points where maximum appears at cosine 1/2 of pi equals plus minus 1. The solution is this one. when we have minimum values, this is 0, pi, 2 pi, and so on. When we have minima, we have half integer. This one should be n plus 1/2 pi instead of this pi should be outside. Okay. In a similar manner, we have no pi inside. As a result, the local maximums, local maxima, and local minima can be completely found in an exact manner from the amplitude, the intensity computation. So this one leads to the phase difference. 1/2 of pi is a multiple of pi. Then vector of 2 is multiplied both sides to find the condition d sine theta equals m lambda for the maximum that we analyzed previously. This path length difference should be multiples of the wavelength, this maxima, and destructive interference appears when we have the path length difference, the d sine theta equals a wavelength multiplied by a half integer. The naive computation is clearly confirmed by this exact computation of the intensity calculation. This is the destructive interference pattern. A pi should be erased. This kind of pattern of bright point and dark point does not happen if we have a different amplitude. When we have different amplitude, the sum of the two waves with different amplitude have additional phase difference, and exact relation appears only if there is a common amplitude between the two interfering waves. It is not a thin film interference, but it is just the interference of standing waves. And reflection. Because the thin film interference has a straightforward technical applications of this theory, we do not consider. Standing wave, let's see the standing wave better than explanation. This is a standing wave. This is a wave This is a wave. It has a wavelength from here to there. This is the wavelength, or this is the wavelength. But important point in this wave is the amplitude. It oscillates. Every point oscillates In here, it does not oscillate at all. This point oscillates. It does not oscillate. In addition, so the amplitude of any oscillation of a fixed point depends on the position. And then, what is the direction of a propagation? Does it propagate to the right or does it propagate to the left? No, not at all. It is not moving at all. It is just standing there. Sit up, sit down, stand up, sit down, stand up, and it does not move to the right. It does not move to the left. So that's the reason why we call it is a standing wave. Actually, the standing wave can be interpreted as the sum of two waves that are colliding, that are making a head-on collision. Let's consider this. We have two waves. One wave equals the two waves of equal amplitude. And we have equal wavelength. K equals 2 pi over lambda. K, they are the same. That means wavelengths are identical to each other. Omega, frequency, period is the same. However, we have a different sign in front of omega t. The velocity of the first wave is, we know, kx minus omega t. Kx minus omega t is usually written in the form 2 pi is a factor down x over lambda minus t over period. So again, we factor k out, then what we would have is x minus vt, where the v speed is wavelength over period. In this case, translation is made to the right. F of x and f of x minus vt. This function can be obtained from this function by translating to the right by amount of vt. That's the reason why we say the first wave propagates with the velocity plus v. Everything is the same for the second. The only difference is the sign. So the upper wave propagates to the right. Upper wave propagates to the right. Lower wave propagates to the left. And they make a head-on collision. There should be energy flow from flow is to this direction, flow is to this direction, because flow is to the left by upper one and to the right by lower one with the equal amplitude. That's the reason why they have exact cancellation of the velocity. So we we compute the interference, the resultant amplitude, resultant wave explicitly. If we sum the two waves, one is sine kx minus omega t, the other is a sine kx plus omega t. So this one can be expressed as kx and omega t for sine kx, cosine omega t minus a sine kx, cosine kx, sine omega t. In a similar manner, the second one has a same term, but opposite sign for the second term. The first term is doubled and second term cancels. So we have factor of 2, additional factor of 2 for sine kx and cosine omega t. In here, x dependence and t dependence are completely factorized. If it were a wave propagating along a certain direction, it should have been kx, f of x minus vt squared, or it's omega prime t, something like that. However, it is completely factored out. It is not in this form, but the product of f of x and g of t. So it is impossible to propagate. Propagation only appears in the form f of x minus vt. That's the reason why the standing wave is not propagating in either direction. Alright. In this standing wave, we have two important points. Here are nodes and antinodes. Nodes are placed where we have position of zero amplitude. We have node. These are the nodes. And we can identify the nodes. This is the full wavelength. This is the wavelength, lambda, and nodes appears periodically with 1/2 of lambda. 1/2 lambda. And there is antinodes. These are antinodes. They are also periodic by 1/2 of lambda. Alright. So identification of the position where the nodes and antinodes can be found by solving these equations. Next, we consider reflections of a boundary at the boundary. Let me show this. If you understand this figure, you understand everything regarding the free end and fixed end. This is a reflection of wave. this is a starting point. This is the starting point. That we do not consider any reflection or absorption or refraction at this point. It is infinity. So the wave is coming in, and there's end. The blue one is called the fixed end, and yellow one is called the free end. The free end is just like a flag, waving flag. And blue one, that is fixed end, is when the wave cannot make any displacement, because it is that end point is completely fixed. We can make use of the collision of two waves by interference. We can reproduce this return. But before we analyze this, we think about the shape. The blue one, after reflection, the displacement it used to be up, but after reflection, it is down. Because it is just like a reflection of a ball against a rigid wall. Action and reaction. The wave wants to hold up the endpoint, but the point is completely fixed. Because of that, to make an equilibrium, the fixed end holds down the wave. As a result, the reflected wave is opposite. It flips the phase by 180 degrees. On the other hand, the upper case, that is for the free end. Just like the wave flag, its wave is natural. However, if you look into the picture at this moment, you can notice that original height is surpassed, and at this time the amplitude is very large, and actually it is doubled. It is almost doubled. So let us see one more time. The reason is that the incoming flow of energy is usually shared by two pieces. The one that has made a displacement already, and the other that is not displaced yet. So two parts share the energy. But however, when we approach the endpoint, there is no material on the right side. So energy coming in and energy reflected, there are some double, but the material, the medium, is remaining the same. The only half of them exist. Because of that, when they make a reflection at the end point for the free end, the amplitude becomes double. And actually, it can be interpreted in a different way, in a very easy way. Free end is a collision of two wave packets. And actually this part, right hand side, is hidden. When they collide, when they reach when they exactly overlap, the two waves, resultant wave is doubled, and only the half, the left hand side is shown. So this part is just like what you have seen previously. At this moment, the amplitude is doubled because of the complete constructive interference between the two colliding waves. In the case of fixed end, it can be interpreted as the collision of two waves. One wave is in this shape and the other wave is opposite. This kind of function is f of x. This one is even function. This even function is for the free end, and odd function is for the fixed end. In the fixed end case, when they collide, because of the odd nature of this function, if we sum the two waves, it is always vanishing at the boundary. So when they meet together, this is coming from the left and the other is coming from the right. They are exactly the same. They cancel exactly. So the resultant wave is exactly zero at this point. But before, this is the central point, just before at this moment, it should have been this and this, right? Although at the boundary, this one is the same, so to have the fixed end, however, the sum of this is not zero, right? It is something like that. Before this point, and after is opposite. This kind of form. So if you flip the up and down, again we can see the difference between the difference of the reflection style for the fixed end and free end. Fixed end, the boundary value is always fixed to be 0. As a special case of a standing wave, we can think of a vibrating string. It can be applied to the instrument, musical instrument, and it also appears in the quantum mechanical bound system. For a given material, the wave propagates with the same speed. So V is fixed according to the tension of the string and according to the mass density of the string. We do not consider the case that the mass density per unit length changes. We do not think the tension changes. So for a fixed tension and fixed mass density, for the linear mass density, the velocity of the wave is completely fixed. and V equals lambda over period. These three cases we can find the wavelengths becomes this is the wavelength. So lambda equals 2L. And this is lambda equals L. And this is the wavelength. Something like that. So inverse 1 over lambda (1 over 2L), 1 over lambda 1 over L. Inverse 1 over lambda is 1/2 or 3/2, something like that. So this is 2L. So this one is a common factor. So we have 1, 2, 3. We say the first one is the first harmonic, fundamental resonance. The second one and third one and so forth. Anyway, because of this, and velocity is fixed, wavelength depends, though, so V over lambda is 1 over period, that is a frequency. So frequency is proportional to this integer with some integer multiplied by 2m. So frequency is proportional to this integer. Because of this, we can find the oscillation. The frequency once this period can be found as 1, 1/2, 1/3. Frequency is 1, 2, 3. 1, 2, 3. As well as the wavelength changes for each distinct resonance state, the frequency depends. Okay, this part will be postponed to the later part. So that's it for today. Thank you.